Hello and welcome to section 5.3, where today we're going to talk about the fundamental theorem of calculus. So we're going to glue everything together and make it one big picture. We've been building on this newer concept of anti-differentiation, and we want to relate that to what we've been doing previously in the course, differentiation. So this concept of taking a derivative or integrating something, we want to be able to link those two together so that we have one nice big picture. And that's what we'll do, and the fundamental theorem of calculus will come in two parts. So when they say the fundamental theorem of calculus, will mean part 1 and part 2 combined. Let's start with part 1 and what it addresses. So part 1 of the fundamental theorem of calculus says if f is continuous on the closed interval a to b, then g of x, which will be equal to the integral from a to x, where for us a is just going to be some real number, f of t dt. So I'm integrating this with respect to t. My upper bound is x. Some people like to write 0 to x, but really this could be any real number, a to x. When I integrate that function f of t, I get the function g of x on the interval, or I should say closed interval, a to b. We'll just write on the closed interval a to b. This function g of x is continuous and is differentiable on the open interval a to b. Again, it's hard to talk about the endpoints when we talk about differentiability. So when we want to differentiate a function at the endpoints, it could be a little risky. So we just sort of leave those out for the derivative. And for us, g prime of x, when we differentiate it, should spit out a function f of x. So in essence, what this means is if I were to differentiate this function, I would get f of x when I'm done. I have an integration here, which is anti-differentiation. So if I differentiate the integral, I get back to the original function f, but I have to respect my bounds. And in the previous section, we saw that these bounds, or these upper and lower limits, were just numbers that we could plug in to evaluate and get a number out of it. Here, x isn't a number, x is a variable, so I still need to be able to plug that variable into my function. So what this is saying is if I differentiate both sides of this, obviously I get the derivative on the left-hand side. If I differentiate the integral, I get the function back. So that is part 1 of the fundamental theorem of calculus. Here's it in an example. Let's say we want to find the derivative of g of x is equal to the integral from 0 to x square root of 1 plus t squared dt. All right, so let's say we want to find the derivative of this function g of x. All spaced out there. There we go. If I want to find this derivative, then all I have to do is differentiate this using the fundamental theorem of calculus. And again, in this case, this is part 1 of the fundamental theorem of calculus. There's a second part coming later. So g prime of x means all I have to do is differentiate this function. On the right-hand side, when I take the derivative, I get the function, but instead of that function being a function of t, it becomes a function of x. Now here I just have the variable x to worry about. So when I do that differentiation, all I will get is that simple, function where t has been replaced by x. I'm replacing the variable. I'm not replacing this variable t with a function that's more involved. I'm simply replacing a variable with a variable, so chain rule is not going to contribute anything there. We'll see that we can extend this a little bit using chain rule, and it actually doesn't really become that hard. It doesn't become much more difficult. So I'll show you an example of that as well. So let's say we want to find the derivative of g of x is equal to the integral from 5 to x to the 5th of secant of t dt. So here it becomes a little more involved. This isn't just the variable x that gets replaced into my function. Now I have to respect some more stuff. I have to respect chain rule. So g prime differentiated with respect to x is going to be me differentiating this integral. I'm going to write out a little intermediate step here. Now, so I have to differentiate this integral with respect to x. So what I'm going to do is fit it into this theorem by rewriting this as the derivative. Since I have x to the 5th, what I'm going to do is look at this as u, some sort of variable. And then when I differentiate that with respect to x, I now have to worry about chain rule and multiply by du dx. Because I'm not simply differentiating and plugging in a variable u here. G prime is a function of x. So ultimately I'm going to have to plug x to the 5th back in here, which is why I need the derivative of x to the 5th, which is 5x to the 4th, to be multiplied on. That's chain rule. So that means now I can go ahead and fit it into the theorem. This u is going to go in place of t, and I'm going to get secant of u. But when I replace this function simply as a function of u, then I also still have to worry about multiplying by du dx, because this is going to contribute more than just the variable x in my function. It's going to give me secant of x to the 5th, which means I need to multiply this entire function by 5x to the 4th. So that would be the derivative of g. And again, it's just more complicated because instead of the variable x, and of course here, it's really not popping up, but when you plug x into the function, you also would apply chain rule, but the derivative of x is just 1. So multiplying by 1, chain rule doesn't lend anything new. But since I have a function that's actually x to the 5th, which is a power function, then I have to respect the fact that chain rule still applies. Whenever I differentiate something, I have to be wary of chain rule coming into effect. All right, so no matter what function you differentiate, you should always be checking for chain rule. So part 1 basically says we can differentiate an integral and we get back to a function. And of course we can integrate a derivative as well to get back to a function. So as long as we can link those two together, then we've got the full-blown calculus at our disposal. So that's what we'll do now. We'll switch gears to part 2. And like I said, when we combine both of these parts, we get the entire fundamental theorem of calculus part 1 and part 2. So part 2 says, if f is continuous, on the closed interval a to b, then the integral from a to b of f of x dx is going to be f of b minus f of a, where I'm using capital F to denote the antiderivative of the lowercase f function, where capital F is any antiderivative of f of x. So we saw back in section 4.9, when we took a general antiderivative, we had this plus c concept. Well, we're not going to need that plus c to pop up explicitly here. What we're doing is we're finding a general antiderivative, which is this weird capital F function. It'll still be a function of x, because that's all we're dealing with here is a function of the variable x. But when I do that, I get a very general antiderivative, something that has a plus c. But then I'm going to subtract that same antiderivative with this other lower limit plugged in, and it's going to have a plus c, but I'm subtracting it all. So I'm going to end up having a plus c and then a minus c. So we actually get to get rid of that arbitrary constant when we do this, which is very nice because now we don't have any vagueness left behind. So this is pretty powerful stuff right here, because now this lets you start solving integrals, which is what we're going to do for the rest of the class, basically. And then as soon as you get into calculus 2, that's all you're going to do. All exam 1 is just integration techniques. Exam 2, more integration stuff. You go into calc 3, you'll be integrating all throughout calc 3. If you take differential equations, you'll be integrating things left and right. So this is really, really powerful stuff. And it also lets us get away from having to do those really tedious Riemann sums. Limit as n goes to infinity of the summation from I equals 1 to n of f of xi delta x. I mean, that stuff is really, really cumbersome, really, really tedious to get through. Sometimes those, depending on the function that you have, you might not even be able to evaluate the limit as n goes to infinity of that sum. That could be a really nasty thing to compute. Whereas here, now we can look at solving these integrals. And remember, this is basically the operation it's telling you to do. Integrate this function e to the x from 0 to 4 with respect to x. So when you read this, you would say, evaluate the integral from 0 to 4 of e to the x with respect to x. Some people would even leave that part off and just say, integrate e to the x from 0 to 4. Right? So there are ways you can say it a little bit nicer. But what we want to do is use that fundamental theorem of calculus that says, I need to find a general antiderivative for e to the x, which in my case is e to the x plus c, right? And I need to evaluate it from 0 to 4. Now, some people watching this video, if they know calculus, they'd be screaming at me right now saying, why are you writing that plus c? Well, I want to show you for the first one why it disappears. And then from there on, you'll notice we don't need that actual plus c, because this says any antiderivative. And the antiderivative of e to the x is e to the x plus c, where I'm picking c to be 0. When I say any, I say I'm going to pick the one where c is 0 because that's the easiest. But I'll show you why it disappears. And then I won't be doing it anymore, because this is a definite integral. When you do a definite integral, that plus c is not going to matter. But the second fundamental theorem of calculus shows us we plug in the upper bound, which for our case here, the upper limit or upper bound is 4. So I'm plugging in the upper bound of 4 to get e to the 4. Again, plus c, because it's just a general derivative. Then I must subtract, and you have to subtract all of it, right? Not just the first term. you want to subtract all of it. So now I have the general antiderivative, and I plug in the lower bound and subtract my antiderivative in its most general form, with the lower bound or lower limit plugged in. And you can see now, there's my lower limit plugged in. So I'm subtracting the general derivative with the lower limit plugged in, and I'm starting out f of b, that's f of 4 in our specific case because 4 is our upper limit. So again, I have to subtract those two, which means I have to take e to the 4 plus c minus e to the 0, which is 1 minus c. And again, notice that those c's, I'm not picking specific numbers for them. I don't care what those numbers are. They're the same number. They will always disappear when you have a definite integral, which is great. Because I'll show you in the next example that we do, we're not even going to use it anymore because we've just shown that it's not really going to matter. We're going to end up canceling it out every time because I'm always going to have an arbitrary plus c, and then I'm always going to subtract an arbitrary plus c. And since they're the same c, they're gone. So and you can approximate this, but I would say stay away from it. Just leave it just like that. The exact value of this integral is exactly e to the 4 minus 1. Finished. Right? Whatever that number is, that is exactly the value of this integral. And again, we're just evaluating an integral, a definite integral specifically. We're not talking about area, but area is one of those applications that you can relate this to. You can ask for the area under the curve of e to the x from 0 to 4. It crosses at the point 0, 1. Right, so you could ask for the area from 0 to 4 under the curve of the graph of y equals e to the x, which is the exponential function. And again, that's a really weird shape, right? It's sort of boxy on the bottom, but it has this weird curve. So it's not a rectangle, it's not a triangle. We don't want to sit here and approximate it with like 4 chunky rectangles, or we don't want to compute, 8,000 rectangles shoved in there. We use the Riemann sum and take the limit so that there are going to be an infinite number of rectangles, and eventually we just get the exact area. So that would give us the exact area. But again, they're not even talking about area. This is just simply evaluate the integral, which is a mathematical concept. If you don't see the word area, they don't mean area. They're not asking for area. That's just something that we can relate that concept to. So again, I want to emphasize that because sometimes students look at an integral at first and they say, oh, okay, I just have to find that area. There is no mention of the word area. That is a physical thing that you have to maybe find in a word problem somewhere. This is not that word problem. This is just a mathematical concept. Right? If someone asks you to take the square root of something, all you do is take the square root of something. You don't take the square root of something like say, hey, what's the square root of 4? 2 feet. Where did you just get feet from? Like it just appeared out of nowhere. Same thing here. They're asking you, hey, evaluate this integral. You should just say e to the 4 minus 1. Done, right? No units, no nothing like that. So again, one of the powerful tools is area, but not every integral means area. So we have to just be able to make that disconnection. All right, let's use this a little bit further. Let's say we want to evaluate the integral from 4 to 6, 1 over x dx. So again, to evaluate this definite integral, I go on the part 2 of the fundamental theorem of calculus, and I say, okay, I need to find a very general antiderivative for 1 over x, which means there has to be some sort of function I know such that when I differentiate it, I get 1 over x. Integrating 1 over x should get me back to that function, and that function is the natural log of x. I'm going to put absolute value bars there for now, but it's okay because our x's, our bounds, upper and lower limits are going to be positive, so I'm not going to run into any trouble. Should I put the plus c at this point? No, because what I'm going to do is evaluate this antiderivative from 4 to 6. If I were to bother to put a plus c, I would plug in my upper limit, have this positive c, I would subtract, plug in my lower limit, get a negative c, positive c, negative c is going to cancel every time in a definite interval, so we're not even going to bother writing it. I only wrote it for the first one to show you that it always is going to have that pattern of add it, subtract it. It's never going to contribute anything to a definite interval. And there's a reason I'm saying definite interval, because we will talk about indefinite integrals later, where the plus c does matter. So here is natural log of, again, the fundamental theorem says I plug in the upper limit, and then I subtract. Here is the natural log of, I plug in the lower limit. And again, if you need to approximate it, then you go approximate it. But for right now, we really don't need to approximate it. The only thing you really could do is look at your properties of logs. Since we're subtracting two logs with the same base, we could write this as ln of 6 divided by 4, which is the natural log of 3/2, which is, again, a positive number. That's why I dropped the absolute value. So the exact value of this integral is natural log of 3/2. And then this is where, again, students say, why'd you make me do all that hard stuff with the Riemann sums and taking limits and all that? And we got to crawl before we can walk before we can run before we can fly. So we just got to build that up. Same thing we did way back in the beginning of the course, right? We had to learn how to differentiate using that long process with the limit as h goes to 0 of the difference quotient. We don't have to do that once we get all those nice properties of, product rule, chain rule, quotient rule, power rule, all that good stuff. It got easier. Same thing's happening here. It's getting easier. So let's take a look at evaluating from 0 to pi over 4 secant squared of x dx. So again, fundamental theorem of calculus will have us evaluate this thing really quickly. So I've got a lower limit of 0, upper limit is pi over 4. I need to find some function whose derivative is secant squared of x, so I can tell that the antiderivative of secant squared is, tangent of x. If I differentiate tangent, I get secant squared. So if I anti-differentiate secant squared, I should get the tangent function to pop up. And then I have to evaluate that function from the lower limit to the upper limit. So again, this vertical bar notation, we've seen it before where we just had to plug one thing in. Now when you see it with something up top and something on bottom, what it means is you plug in the upper limit of integration, and then you subtract the lower limit of integration, because that's what the fundamental theorem of calculus tells you. F of b minus f of a, there's b and a, b and a, b and a. So you always do the upper limit plugged in, and then subtract the lower limit plugged in. Okay, so now we just have to go back to our trig and say, tangent of pi over 4, right, that ratio is just 1. Tangent of 0, that means we're not going anywhere here. And we're in radians, so that's 0, so I just get 1. So even though you may look at the graph of secant squared and it's got a whole bunch of asymptotes, we're not hitting any of those asymptotes, so that's why we're not coming into any weird situations where any problems are arising, and we can evaluate this pretty nicely. And again, we'll start off with the nice functions, and then later on, when you get to Calc 2, you'll see what happens when there's an asymptote in your way, or the function has a bunch of discontinuities or what have you. So for now, we're just kind of building up to some really nice functions that we know their derivatives, so we can work those derivatives backwards, integrate to get their antiderivative pretty nicely, to see some nice applications of part 2 of the fundamental theorem of calculus. Now, let's pick on another one. Let's say we have to evaluate from positive 1 to positive 3. This polynomial 4x cubed, let's do minus 2x to mix it up. I had a plus, but let's put 4x cubed minus 2x. So this is the function I'm looking at, and I want to integrate it from, very specifically, 1 to 3. So that second fundamental theorem of calculus tells me, hey, guess what? You don't have to do all this limit n goes to infinity of this great big sum. Just use the second fundamental theorem of calculus to identify any general antiderivative. Remember, when you take the antiderivative of this function, you would tack on a plus c because there's an infinitely long list of antiderivatives. It could have had a plus 0, a plus 1, a plus 2, a plus pi, a plus e, a plus negative 100, right? But we don't have to worry about that. Thank you, second fundamental theorem of calculus. All I have to do is find the general antiderivative minus find the general antiderivative and evaluate this general antiderivative, which is one of the antiderivatives. It just happens to be the antiderivative with a 0 constant, from the lower limit 1 to the upper limit 3. And again, when I look at this, the notation is just telling us, hey, integrate with respect to this variable x. So I don't need all that extra stuff left over. Some people will integrate and then leave the integration symbol. That would be like me taking the square root of 4 and saying, that's square root of 2. That's not true. Well, you don't need that symbol anymore. Get rid of it. You've done the operation. No need to show me that you still need to do the operation. So same thing here. That's why that integration symbol and the dx symbol are being dropped. And now we can just straightforward plug in what we need. Now, don't make the mistake of saying, oh, I'll plug in the upper limit 3 here and the lower limit 1 here and be done with it. No. The second part of the fundamental theorem of calculus says you plug the upper limit into all of this. That is the general antiderivative with the upper limit b plugged into the function. And then you subtract all of this, plug in 1, 1 to the 4th minus 1 squared. All right, so some people do this. They'll say, oh, I'll just plug the 3 in here and subtract the 1 squared, and I'm done. Well, then you haven't properly plugged the upper limit into the entire antiderivative. You haven't properly plugged in the lower limit into the entire antiderivative and then subtracted that entire lower limit plugged into the antiderivative. So make sure you get everything into that function where it needs to be across the entire function, then move on to subtract the lower limit. So 3 to the 4th is 81, minus 3 squared is 9, minus, well, this is just 1 to the 4th minus 1 squared, so that's just 0. That part's not going to contribute anything. And 81 minus 9 is going to be 72. And again, these are definite integrals, so when we evaluate them, we should be getting some sort of finite value out of them. Now, we do have to be careful, and I just want to mention this, not that you'll probably come across this a lot at this point, but you'll come across it a lot more later, like mostly really when you get to Calc 2, you'll come across integrals like this, where you have to do a lot more. But right now, I just want to kind of throw out like a fair warning of you can't evaluate every integral now. There's no way that, since I've given you this fundamental theorem of calculus part 1 and part 2, that you now have a free pass to integrate everything under the sun. Where there's still some things that we have to be careful about. So here's a quick example. If we want to integrate from -2 to +4, 1 over x squared dx. You might find yourself in a situation saying, oh, I can do this. This is me integrating from -2 to +4. We'll look at 1 over x squared as x to the -2. Now, again, be careful. You need to find the general antiderivative of this function. Don't tell me that the general antiderivative of this function is like log of x squared. Go differentiate log of x squared. You will not get this function out of it, right? So you do have to be very careful. This is just simply going to use power rule. So I'm going to go up a power, which will be x to the -1st. But if I differentiate this, I get -x to the -2. That's not -x to the -2. So if I squeak in an extra negative there, now when I differentiate this function, I get negative x to the negative 2, which is positive x to the negative 2. So this is the derivative, and then this is the antiderivative. So I've got a general antiderivative. I don't mess with the plus c because it'll cancel no matter how hard I try. So I just evaluate that from the lower limit to the upper limit by plugging in the upper limit first. And I'm going to rewrite this as negative 1 over x to the first from negative 2 to 4, which is negative 1 over, I plug the upper limit in, then I subtract the lower limit plugged in, which means I'm subtracting negative 1 over negative 2. So I plug my upper limit in, I plug my lower limit in. There's lots of negative signs flying around in that second piece. So I've got negative 1/4. Minus minus is positive, but then there's another negative in this fraction, so I'm actually subtracting a half. Common denominator says I have a negative 1 minus 2 over 4, so minus 2 over my common denominator of 4. That's a negative 3/4. And you would think, yay, I'm done, I did it. And this is completely wrong. So think about why that would be completely wrong. Maybe you've seen it already. Go back and look at part 2 of the fundamental theorem of calculus. Right off the bat, it says, if f is continuous on a to b, aha, is this function continuous from negative 2 to positive 4? If I graph this function, there's an asymptote right here at 0. So the problem is, since I have this asymptote, I do not have a continuous function from negative 2 to positive 4. I don't even meet the very first criteria of the fundamental theorem of calculus. So I can't apply the fundamental theorem of calculus. It makes no sense. Fundamental theorem of calculus says this has to be continuous on a to b. Well, I've already failed that. If I fail the very first criteria, then I do not pass go, I do not collect $200, I don't get to continue. The theorem does not apply. So I cannot apply it. And that's why I'm getting this answer. It looks like it works, but yeah, of course it looks like it's going to work because all you're doing is just plugging in some numbers into some fractions. You get some fractions, you count them up, you get something. But that's not true in this case. Right? So we do have to be careful. In fact, what's happening here is this integral does not exist. So remember, like back in the last section, when we looked at the Riemann sums, we would say that the limit as n goes to infinity of the sum from I equals 1 to n of f of x I delta x. We looked at all that and we said that is equal to the integral if that limit exists. Right? So that's the problem here. When we look at this, we've got this asymptote in our way. So our function is shooting up to infinity, right? And on the left-hand side, it's coming from infinity, coming down. So we need a lot more tools to be able to evaluate stuff like this. So again, the fundamental theorem of calculus is not just a free pass to integrate everything under the sun, right? So we do have to be careful and make sure it's meeting the criteria so that then we can apply it. Now, there may only be like a very few of these in the exercises where technically you could be led astray if you don't check first to see if it actually can be applied to the fundamental theorem of calculus. But most of the exercises there, you can actually find a value by using the fundamental theorem of calculus. But there are just a couple. I mean, like a handful, maybe less than a handful that you do have to be careful about. You might think you're getting the right answer, but in reality, you forgot to check that criteria to say that you just can't use the fundamental theorem of calculus. But again, there are ways to integrate that. Don't worry, when you get to Calc 2, you'll figure out how to do it. There's a whole lesson on how to deal with integrals of that nature that have this weird asymptote in the way or something like that. So, it's not like it's not like nobody can find that integral. It's just you need the bigger tools to do it. So let's see what else we got. Look for looking for a good function here to integrate. Let's see what we got. So let's say we want to evaluate the integral from -1 to 1 of x to the 100 dx. That's kind of a silly power. But I picked this one in general just to show you something neat. So when we integrate from -1 to 1, x to the 100 dx, you're thinking, wow, that power is crazy. Well, don't worry. General antiderivative is going to be x to the 101, but I need to divide by 101. Because again, I want to be able to differentiate this function. So if I just differentiate x to the 101, I get 101 times x to the 100. And that extra multiple of 101 is not part of this function. So this is not the general antiderivative for x to the 100. But if I have this division here, then I differentiate this, I would get 101 times x divided by 101, and then I would subtract 1 from the power. Ah, those cancel out now. That is the general antiderivative for this function. So again, be careful, make sure you're actually getting the correct antiderivative. Otherwise, there's no reason to move further and plug those bounds in if you don't have the correct antiderivative to begin with. So this isn't terrible because we're just dealing with this weird power of 1 to the 101 divided by 101 minus -1 to the 101 divided by 101. Right? So I plug in the upper bound, or the upper limit, which is +1. And then I subtract the lower limit plugged in, which is -1 to the 101 divided by 101. Yeah, it's kind of silly. They have this common denominator of 101. 1 to that positive power, 101 is still 1. -1 to that odd power means I'm subtracting 1. Or I'm sorry, I said it wrong. I'm subtracting -1 because -1 to the 101st, that's an odd power, so that's negative, and I'm subtracting a negative. So I'm actually adding to get 2 over 101. Now, I wanted to just show you kind of briefly that we had a bunch of properties for integration. One of those properties was if we integrate from a to b of some function f, what we could do, as long as f was continuous on that interval a to b, we could break it up at some number, say n, so that rather than going straight from a to b, we could go from a to n and then pick it up n to b. So basically what we're doing is instead of finding like one fell swoop a to b, we're going a and then we're stopping somewhere in the middle and then we're picking right back up where we started and going from n all the way to the end. And then just kind of adding those two values together to get the total value of the integral. So we were able to use that. What I'm going to do is I'm going to say, well, this is an even function. Right? Y equals x to the 100, since it's an even power. This is what we call an even function, which means it has y-axis symmetry. Right? So it is symmetric about the y-axis, meaning that when I integrate a function like this, right, it's going to have the same symmetry to the left and to the right. Now, the graph of x to the 100 shoots up very sharply, so it's actually steeper than this, but I'm just giving you an idea here. Notice when I integrate from -1 to +1, I'm actually getting twice of this, and again, I'm relating it to area, but this is not talking about area. This is just the concept of the derivative. But we'll be able to use this nice even feature here to say that will give me 1 over 101, that will give me 1 over 101, and then I combine them to get 2 of those over 101. So the nice thing you can do about integrals is you can use this really nice feature to say that since this is an even function, I could rewrite this integral as 2 times 0 to 1 x to the 100 dx. Now, I often don't do this, every time, even if it is an even function. Sometimes I just integrate it and be done with it. But there are times where I say, ooh, I don't like those upper and lower limits. I know it's even, aha. 0 is the way easier lower limit to plug in, so I'd rather compute it this way, but I do need to double it, because here I'm going from -1 to 0 and then 0 to 1 to get that value. But because -1 to 0 and 0 to 1 are going to give me the same value, then I'm just going to double one of them to be done with it. So there are some nice tricks that you can use to help speed things up and then evaluate this from 0 to 1. That would mean I'd have to double 1 to the 101st power over 101 minus, now I have to double all of it, so minus 0 to the 101 over 101. Again, I just have to double everything. That's gone. That's just 1 over 101, so that's 2 over 101. So there'll be some nice tricks that we can use to our advantage to evaluate some integrals nicer. But you can see either way I do it, even if I don't do this trick, I'm fine. In fact, if you try to use this trick where you can't, obviously you'll get yourself in danger. So for now, you'll probably just want to go right for it without trying to mess around with this tricky stuff. But a trick like that will be useful when we start talking about area. And we've already seen it when we tried to find the area of like the upper quarter of a circle in quadrant 1. Right? We looked at that and we said, oh, that's just a circle and I have the formula for that. Rather than find the whole thing, let me just find a quarter of that whole area. I'm doing sort of the same thing here, but I'm finding half the area and then doubling it. But again, if we're not specifically talking about area, then we don't want to say that word anymore, so we'll get away from that. But we still can use the even nature of that function. Let's see what else we have. Let's do this one. Evaluate the integral from 1 to 18 of the square root of 13 over z dz. Why are they picking z? Who knows? But they are. But at least they're telling us, hey, z is the variable, so you're going to integrate with respect to z. So basically what we're doing is we're trying to pick up f of z. We're trying to pick up a function of z. Now, don't be too scared just because this looks a little weird with that radical 13 over radical z. Again, I can break it up. I can take the square root of the top and the square root of the bottom. This is just a multiple, and again, another one of those properties that we had for integration was if I just have a constant multiple, I can pull that multiple out front of the integral because it doesn't have anything to do with the variable z. So either I multiply by radical 13 first and then integrate, or I integrate and then multiply by radical 13. I'll still get a radical 13 multiple of the integral. So either way I do it, I'm fine. So that shouldn't confuse us when we go to integrate this. This also, when I look at it, I have to come up with some sort of general antiderivative for this 1 over square root of z. Remember that notation with the radical bar like that, not helpful. We want to see a power because we want to find a general antiderivative. And again, don't you dare tell me that this is log of square root of z. Right? There is only one integrand that we find that should provide us with ln of z. and that is this integrand, 1 over x. Right? If it was 1 over z, it'd be log z. But that is not z, that is square root of z. So since it's not this form, I don't use anything to do with the log. I use the power rule. And this is really z to the negative 1/2 dz. So don't integrate and add 1 to a half. The power rule doesn't allow you to do that while the power is in the denominator. When the power is in the numerator, it allows you to do that. Add 1 to this power, and adding 1 will give you positive a half. Adding 1 to this gives you 3 halves. That's definitely not the antiderivative, because if you differentiate it, you will not get this back. But if I differentiate z to the 1/2, then I'll be okay. But the problem here is if I differentiate z to the 1/2, I'll get 1/2 z to the negative 1/2. This is not 1/2 z to the negative 1/2. So in order to fix this, I'm going to have to multiply, well, let's do this. I'm going to have to divide by whatever that new power is, which is 1/2. And I'm going to integrate that to get this. Now, give it a try, right? Differentiate this to see if you get z to the negative 1/2. The multiple of root 13 is obviously there, so it's just sitting there. If I differentiate this, dividing by a half is really multiplying by 2, which is good because now when I differentiate this, the half times 2 will disappear, just be one of these z to the, subtract a power, that's z to the negative 1/2. So again, by differentiating this, you should get this. Because when you integrate this, you get this. Again, it's just a simple back and forth. You can jump back and forth all day long. Differentiate this, integrate this, differentiate this, integrate this. You should never get anything different. If you differentiate this and you do not get this, then you have already gotten the wrong antiderivative. And like I said, there's no reason to move forward because you did not get the correct general antiderivative. In this case, we're good. We can see it. I'm going to leave the root 13 all the way out front. I'm going to plug my upper bound in. So instead of dividing by a half, I'm going to multiply by 2 times z to the 1/2. Well, that's the square root of z, but I have to plug in my upper limit. So I'm getting 18 to the 1/2 power. Then I have to subtract. Now I plug in my lower limit. Again, instead of dividing by a half, I'm going to multiply by 2. Z to the 1/2 is 1 to the 1/2 when I plug the lower limit in. Now we can start to simplify this. So I've got root 13 still just chilling out front, being multiplied to everything because that's where I put it. I've got 2 times the square root of 18, right? That's really 9 times 2. I can take the square root of 9, which is 3. 3 times 2 is 6. Root 2 minus 2 times root 1 is the same thing as 2 times 1, so I'm simply subtracting 2. All in all, we'll have 6 times the square root of 13 times the square root of 2. Well, unfortunately, there's nothing we can do there. 2's prime, 13's prime. They don't share any common factors, so I'm going to fudge them back into one radical. Minus 2 root 13's. Now, there's nothing I can do to add these two together because they don't have like radicals. So I can't do the addition or subtraction in this case. So this is my final answer. Kind of a weird answer, but is what it is. They gave me some kind of weird numbers. If that was a 16, that would have worked out a lot nicer. Now I'm just curious if it was supposed to be a 16 and it wasn't, so I copied it correctly and just give you a weird answer. Let's see where we're at here. I think we'll squeeze in. Let's squeeze in one more. But again, these integrals come in all different, forms, all different types of functions. You might be integrating a polynomial, and you might be integrating a trig function, and you might be integrating an exponential function. So there's just all different kinds of functions that we can integrate. So practice as many as you can. Let's see if we can pick on here's a funny one. And the only reason I saw this one, that it doesn't look complicated, but the only reason I saw this one is because this will catch some people the first time they try and do it. Right? They're going to say, ooh, I integrate this, I get e to the x, and then I start plugging my upper and lower limits in. E is just a number. So again, this is telling you that you are integrating this number. And we had a property that said, if we integrate c from a to b times dx, we just get c times b minus a. Right? We're just basically getting that interval back and multiplying the length of that interval times that c. This is not a function e to the x. This is simply a number e. So in order to evaluate this, I just do e times the length of the interval, which is the upper limit 5 minus the lower limit negative 5. 5 plus 5 is 10, so this is 10e. Seems kind of silly, right? So really what we're doing here is we're taking an interval from a to b of just some constant multiple. Since it's a constant multiple, it really has nothing to do with the derivative. I'm basically integrating the number 1. And when I integrate the number 1, I'll get back my x. When I integrate the number 1, I get x back because the derivative of the variable x is 1. And then I have to evaluate that x from a to b, which means that constant multiple just sits out front, multiplies everything because that's where it is. It sits out front, multiplies everything, and I have to plug in my upper limit for x, and then by the fundamental theorem of calculus, subtract that lower limit of a. So now you see where we're getting this from. In the last section when we talked about properties, we can see that all we're doing is we're integrating just some number. So all we do is get back that number, but we also have to multiply by the length of the interval in order to get the proper value for that definite integral. So again, that one's kind of silly. But I just want to say that, that could catch someone off guard. They see the number e, and for some reason they automatically say that's e to the x. E is just a constant. E to the x is a function with a variable x. So we do have to be careful and separate those two. And then let's do... So I know what I want to do. That's a pretty good amount of examples there, but I do want to just touch on maybe one more from 0 to 4. 4 minus t times square root of t dt. Again, the variable is very important. It's not always going to be x. Right? If they're telling you that you have a function of t, then when you find the antiderivative, you should get a function of t. And that's why this dt is very important, because if that said dx, then none of this gets integrated, which is really silly because this is all a function of t. If that says dx, then you don't integrate this stuff because it has nothing to do with x. So that's why that is very important and should be there. Lots of students tend to get lazy and leave it off, and then what you're writing is, again, becoming meaningless. We don't want it to be meaningless. We want it to be very meaningful. So I have the product of two functions. Now, you'll notice that when we integrate, we don't get a reverse product rule. We don't get a reverse quotient rule. We don't get a reverse chain rule. What we'll do is in a later section, we'll figure out a way to handle some nastier functions that we need to integrate. But for right now, we don't have a way to undo this. And again, look at your properties for integration. You never got this property, and you never will get this property. Again, think about when you differentiate. When you differentiate the product of two functions, you don't just differentiate the first and multiply it by the derivative of the second. That's not product rule. You're not getting the correct derivative. Well, the same thing applies for integration. When you find the antiderivative, you can't just integrate this and then multiply by, I'll integrate that and get the proper antiderivative. you're wrong, because if you try and differentiate that, you will not get this product of functions back. So we don't get this. That's just a really big does not equal sign. So we didn't get that property, and there's a reason we did not get that property, because that property will never be given to you. It's not going to be true. And oh boy, you get in a very specific situation where it is true. One example of it being true is called being very lucky. That's not a proof. That's not a property. It's called you got lucky. So 99 times out of 100, that never works. I would say even more times than that. But nothing's stopping us from doing the algebra. Right? Nothing is stopping us from saying that inside here I have 4 times t to the 1/2 minus t to the 3/2. Nothing's stopping us from multiplying this out. Again, this is t to the 1/2, so there it is. T to the 1/2 times t to the first power. I add the powers to get 1 plus 1/2 is 3/2. And again, I don't like the radical bar notation because I need to be able to integrate this thing, meaning I have to be able to add 1 to that power and divide by that new power. So when I do this integration, I'm going to have 4 times t to the 3/2, but I need to divide by 3/2 in order to make sure that when I differentiate this, all I get left is 3/2 t to the 1/2. So if I divide out by that 3/2, then I just have the multiple 4. Minus, I need to add 1 to this power, which is t to the 5/2, which means I need to divide by 5/2. Little correcting factor here, because again, if I differentiate t to the 5/2, I would get a multiple of 5/2 t to the 3/2, but there is no multiple of 5/2 here, so that's why I need the division by 5/2. So when I differentiate, the multiple and the division cancel each other out, and I just get t to the 3/2. This is a general antiderivative for this integrand, meaning this integrand here I have properly integrated, and I evaluate it from 0 to 4. So again, we'll start by plugging in the upper limit of integration. So we have 4. Actually, let me move down here where there's a little more space. We have 4 times 4 to the 3/2 divided by 3/2. Rather than divide by 3/2, I'm going to multiply by 2/3, the reciprocal, just to make it a little cleaner. Minus, now I need 4 to the 5/2, and instead of dividing by 5/2, again, I'll multiply by the reciprocal. Now this is my upper limit plugged in. So now the fundamental theorem of calculus says I subtract my function with a lower limit, 0, plugged in. So here is 4 to the, again, instead of dividing by 3/2, I'll multiply by the reciprocal 2/3. I need t, which is in this case 0 to the 3/2, minus, now I need to plug 0 to the 5/2, and again, instead of dividing by 5/2, I'm going to multiply by 2/5. Now the really nice thing about this, and of course it's because of the number 0, my favorite number, that's 0, so this whole thing is 0, so I don't have to worry about that at all, because that is only going to have me subtract 0. Who cares, right? So this is the thing that I'm really concerned about. So I figure all this out, and then I subtract 0. All right, I'm done subtracting 0. Let's figure all this out. So 4 times 2/3, that's just 8/3. 4 to the 3/2, remember this is the square root of 4, which is 2, cubed, which is 8. So I'm doing 8/3 multiplied by 8, minus, there's 2/5 times, again, 4 to the 5/2. That means I'm taking the square root of 4, which is 2, and then raising 2 to the 5th power, which is 32. So now I've got 8 times 8 over 3, which is 64/3, minus 2 times 32 over 5, which is 64/5. So again, these are like 8 over 1, 32 over 1. Right? So I'm just getting something nice there. So now I've got a common denominator of 15. Unfortunately, that's the best that I can do. So I'll multiply this by 5, top and bottom. I'll multiply this by 3, top and bottom. So I'll get 64 times 5, which is 320. And then I'll subtract 64 times 3, which is 192. I'll have a common denominator of 15. We'll get 320 minus 192 is 128. And divide that by 15. And I don't really know if we can do anything with that. Let's see. Definitely 2 doesn't go in there. 3 won't go in there because 8, 9, 10, 11, right? The sum of the digits here isn't divisible by 3, so not divisible by 3, definitely not divisible by 5. Those are my only choices here, 3 and 5, so I guess we'll circle that and say simplified. So, there's a good bunch of examples. So, this is the main thing that we're going to be doing for the rest of the course is integration, integration, integration. And then, of course, Calc 2 picks up. Next chapter is just, okay, you learned how to integrate, basic functions. When you get to the first part of Calc 2, they're going to say, here are the more complicated functions and a lot more complicated techniques. So right now, it's very straightforward antiderivative. Basically, what we're doing is applying things like power rule, or we're looking at very specific integrals like 1 over x or the exponential function e to the x. Right? We're looking at very specific integrals because they have very specific antiderivatives, or trig functions have very specific antiderivatives. So we're being careful about the functions that we're giving you. We're being careful about the functions that we're picking so that we're staying safe. But trust me, it gets a lot more fun as it keeps on going. So that's 5.3, really, fundamental theorem of calculus. Lets us now go back and forth between differentiating and integrating. So we've connected those two concepts together. So for the rest of the course, practice your antiderivatives. That's going to be a very important step to get the proper integral. And of course, a lot of this stuff is going to come down to just basic algebra, arithmetic, really. This isn't even really algebra at this point. It's lots of arithmetic. So don't worry and spend so much time on this junk, right? Really, it's this junk here where it's finding the antiderivative, making sure you're plugging in those upper and lower bounds properly. And hey, before you even bother with that, there's a few in there, like I said, check, make sure you can actually apply the fundamental theorem of calculus. Make sure that function is actually continuous, like this one is, and you can plug 0 into the square root, you just get 0. Right? So we do have that continuity. So practice these up. And then we really only have 2 more sections, 5.4 and 5.5. 5.4 deals a little bit more with applications, and then talking more about area quite a bit. And then 5.5 focuses on the substitution technique, which is, like I said earlier, we don't have a product rule, a quotient rule, or a chain rule for antiderivatives right now. The substitution rule is going to help take care of that stuff. So we're going to need that in the end to help take care of some more complicated functions. Keep practicing, and I'll see you for 5.4, and after that, 5.5. Thank you.